Hurst. I'm the founder and CTO of CineCert, a small consulting and software publishing organization in Los Angeles that was founded about 17 years ago to work on digital cinema standards. We were around at the very beginning of IMF to get that up and running. We participated in a lot of the SMPTE standards process to get IMF published and working. And of course, we've been following along with all those specs in our implementation. Here today to talk about a piece of the IMF road landscape output profile list that hasn't been getting a lot of attention, but I hope we will get to in the next couple of years. We'll see some good solid forward motion on this topic. So the reasons for the work that I'm doing right now, I like it. So that part is interesting. Hopefully it pays the bills. I do have some customers who have an interest in this area, but for a lot of people, it's not quite clear yet why this is an important standard. And I'm hoping to highlight that with today's conversation, in addition to showing the work that I've achieved. And then lastly, closure. Is about seeing through the project that we started. IMF packages are interesting in and of themselves, but their true value shows up at the head end of an automated processing environment. And OPL is the interoperable expression of that automated processing environment. You can use or have either one of those things, the package or the processing environment, without the other. But there are, billions of use cases that grind against that create all kinds of pressure. And the whole motivation for this project in the first place was to have automated processing of large libraries of information, and OPL is that bit. So if by analogy we say that the IMP is the shipping container, then the OPL is the modern automated seaport. Sure, you can have modern automated seaports with old clipper ships, but they're not really very interesting. And you can have large container ships without seaports, but they take forever to unload. But when you use the two together, you get an increase in scalability that goes beyond anything that has existed before it. And just to continue to abuse this analogy a little bit, what I'm showing you today is the first seaport with one crane. The container yard is only half paved, and we're using a couple of diesel trucks instead of electric robots on the ground to move containers around. So it's primitive days here, but the future is visible on the horizon. So what we're talking about here in terms of the scope of the work that I've been getting into here is applications 2, 4, and 5. And the existing published set of output profile list documents. If you're not familiar with OPL documents, they don't take very long to read. And in fact, if you read them by themselves, it's kind of hard to see how it all really works unless you have a firm mental model of what the IMF package data model is. So browse those, but then I'm hoping that this talk is going to be one of a series of talks I'll give this year. This is sort of the hastily assembled outline. I was just asked to do this last week, so the slides are full of information, but not full of interesting graphics. But hopefully with comments and repetition, this will become a much more interesting and provocative proposal. So we're starting with this scope. And the idea is to map that stuff onto a territory that everybody should know by now, which is I want to run it on AWS or its like, or I want to run it locally. I'm probably going to run it on Linux. In our case, Python and C++ are our primary implementation languages, so that narrows down for us what the territory is. So our immediate goals are to transform at4 DCDM into DCP. This is the goal that kind of really put the spurs to doing this work. We've been participating in that community for quite a while, and the whole point of having at4 DCDM is to be able to make DCPs out of it. It's inherently automatable because it's an IMF, so it seemed like a good place to grab on. That, in addition to our very long experience in DCP, makes it very easy for us to see what that transformation looks like and account for all the steps and not be too surprised by the arcane reading that's necessary to get into that. App2E isn't too much different, except that you have to mess around with color and audio routing a little more. And then time text is a completely different beast in all the applications except for App4 DCDM. I'm not going to talk about time text today, but if you actually wanted to go from TTML into the digital cinema domain, you'd have to do a mapping that I don't believe exists as a standard anywhere at this time. App5, of course, is a common application, or wants to be a common application in cinema. Certainly ACES is becoming more common, and wrapping up ACES into App5 was not complicated. So we hope to see more direct transformation from application 5 into DCP this year. And then all this improves our products overall. We have a fairly deep set of library and component products that people can use to build customized workflows. And this just gives us more modules and more interesting capabilities to play around with. One example of a module that's portable is the general concept of mapping from some set of audio sources into MXF using 377-4 labels. That module can exist, certainly has to exist in OPL, and can be used a la carte as well. So we're looking forward to being able to map new capabilities into our existing tools in addition to adding OPL capacity. So we have several runtime behaviors that we have to support. Usually everything in our company starts life on the command line because that's where we can think about the process and not spend a lot of lines of code on interface. But eventually it has to be available on a server as an autonomous process. And eventually somebody just wants you to run that server as a service so they don't have to deal with the system administration themselves. And then finally, for scalability, everybody eventually says, well, can't I just have a Lambda? So all of this development is designed to fit into this continuum of very personal to global scale as end users' requirements dictate. So what we're using from the existing published OPL that's working, preset works, we recognize them, but they're hardly any OPL at all because it's just a label. And without the definition of what that label means, it really can only be used to communicate information in a portable way between agreeing partners. So the transportation of the information is portable, but the meaning of it has to be agreed upon out of band. So we handle preset, but we don't actually currently map any preset URIs onto any specific processes, and hope that we never have to, because there's a much better way to do it. PixelDecoder and PixelEncoder are in the 2067-100 series of documents. They're in 101, I believe. These are the macros that convert from the integer or floating point encoding that's in the actual MXF file into the reference pixel processing space that's defined by the OPL. For those that are not familiar with that, OPL provides a way to encode and decode from the various numerical formats that you'll find in all of your image file documents. But rather than defining processing in terms of all those different potential coding schemes, instead we have an internal reference pixel, which is a normalized floating point value. And the general concept for OPL processing is that you convert into that reference pixel, do some work, and then go back out to some other kind of coding for your output. And we'll see in more detail how that works as I go on. Image crop worked, and audio routing and mixing works, with the exception of one typo that I found in the audio routing and mixing spec that's already been fixed. All these things work as advertised in 2067, 101, 102, 103. So good job, team, for hitting the mark so well, despite a lack of implementations to prove efficacy as we moved along. Hopefully that is going to change. So what's missing? There are no macros currently published that define how you get out of the OPL into something. That's been a large focus of my effort here. There are no macros that support color transformation. So those pixel encoders and decoders will allow you to go between different transfer functions and numerical encodings, but they won't allow you to change your color cube from one domain to another. So there's no macro for that yet. And to do, for example, app2e into DCDM, you're going to have to perform a color transformation. There's also no discussion about the announcement of process state. So one of the things that happens when you have a remote process is that when it fails, you want to know why and how it failed. And it happens a lot that you receive failure messages that are written by an application designer who is merely making use of a library, and they're giving you their own message, and what happened actually down in the library is hidden. So one of the things that I want to try to promote throughout this project is a portable way to communicate OPL failure state back to the responsible party. So this would mean, for example, one of the things that we're working on internally is a list of named exceptions, for example, that could be reported by a system so that again, a third party who doesn't know the actual details of a particular system can at least recognize the error messages that are related to this process. We'll talk more about that, hopefully in the coming months as we do some more work on this project. So our basic signal path as currently published is we have a CPL, and it has virtual tracks, and those virtual tracks are selected by macros in a directed acyclical graph that should look familiar to anybody who's worked with any media encoding equipment that has a GUI and allows you to arrange a signal path. So this very simple example here would decode the image pixels, re-encode the image pixels, perhaps into a different transfer function or a different bit depth or a different pixel structure, and then output that to some place. And really briefly, what that looks like in XML is we have a giant collection of schemas that we need to bring in, because one of the interesting bits about this project is that it's defined, it collects the work of other projects as well that are also defined in XML. And I gotta say, I'm really impressed with how easy it is to compose other projects into the OPL project using simple XML technology. This has been kind of fascinating, actually, and how well it's all gone together. And the real, I think, shining example of that is audio labels, which we'll come to in a little bit. This is an unparsable, non-functioning, bogus XML version of an output profile list that exists only to show its sort of essential features. There's an aliasing mechanism that allows you to use small names to refer to CPL virtual handles. Here's our PixelDecoder type. It doesn't have any properties because the design of the PixelDecoder type is that it reaches out to the metadata in the source MXF file and figures out transfer function, bit depth, and color chromaticities from the descriptors in the MXF files. So there's no need to say here what the color is. We're going to get the color that we're supposed to get by decoding according to the metadata in the file and producing a reference pixel in the normalized space. The PixelEncoder does have a color encoding value that's used to configure it. These values all come from the schemas, the OPL schemas, and from regXML. So there's a large catalog of values to play with, and what's nice is that these systems can be expanded by simply increasing that universe of values. So I'm using ULs. I actually spent quite a bit of time plugging new ULs into my system because I was using stuff that I hadn't used before, and had to actually go out and find the ULs and bring them in so that I could use them. I'll talk about that next macro in a second. I'm going to go back to the discussion about nothing on the output side. So we've been thinking quite a bit about specifically when you want to make a digital cinema package, there's a bunch of information you have to collect together. And it's not just a matter of potentially manipulating the image. It's not just a matter of routing audio signals. We need to know about certain metadata that goes in the CPL. We need to understand how exactly we're going to pull edit units from the IMF side over to the digital cinema side. There's a lot of detail that has to be sorted out. And in order for that to actually be useful in the world, it needs to be written down in a way that is interoperable and portable. So we've created what we call a terminal macro, a DCP terminal macro. We call them terminal macros because they terminate the right-hand side of the graph and have no subsequent edges that go to the right from there. So it's inputs only. In the OPL study group last year, we had some discussion about something we were calling an output macro. But when I wrote the sentence, output macros have no outputs, I realized that I really would like to call them something else. So that's where I came up with terminal macros. So we have developed a terminal macro internally and in conjunction with some of our colleagues in the industry on an informal basis to try to move this process along. And we hope that this will soon become a project we can work on in the standards community, but we're going to get some more functionality underneath it before we get any further. So back to the abbreviated OPL down at the bottom here, we have our terminal macro. And just to kind of highlight how this works, so the terminal macro is selecting, whoops, excuse me, I meant to click where I can't, I guess. The handle here for the source image sequence is this DCDM int12 macro, which is the name of this macro here, whose handle is the DCDM int16 macro, whose name is here, whose handle is the image source, whose name is here, whose handle aliases back out to the CPL virtual track. So this is the statement, if you will, of the signal path between the frames in the IMP filtering down through a process into the input of the terminal macro where they're going to get processed and further turned into some artifact. So what is a terminal macro? It's a defined endpoint in the graph. It's a macro in the full sense of an OPL XML structure that inherits from the orthodox hierarchy, but it does not produce any output signals that can be consumed by anything else in the OPL document itself. Whatever it produces is unique to its implementation, and it's up to the implementation to decide whether those things are going to go into S3 or onto a file system or wherever. So the terminal macro collects all the parameters we need. So in the case of CPL, in the case of DCP rather, we need to know things like which DCP profile we're addressing. We need metadata to go into that CPL. We need to arrange audio channel labeling so that it's correct and so forth. And so this document provides that expression. And in our implementation, we actually make it possible to have multiple terminal macros. So you could, in addition to, for example, the digital cinema package terminal macro, if you wanted to also output, say, a WAV file that contained the composed audio from the IMF world, we could invent a new terminal macro called the WAV PCM terminal macro. And there's no reason why it could not exist simultaneously in the same instance of an OPL. But right now we only have the one, although we are designing for multiplicity all around, because the question still remains about what should be the scope. So we've taken a kitchen sink approach here where we have one macro that understands how to make multiple MXF files, the cinema track files, and the cinema CPL. And in doing that, it's fairly straightforward to hold together all the things that we need, because not only does the CPL have to refer to all the MXF files that we made, but for example, if those MXF files were encrypted, there's some tie-in between them. So it was easier to make that macro monolithic, if you will. But there's also the argument to be made that instead what we should have is a series of highly flexible output or terminal macros. So for example, an MXF terminal macro that could make any operational pattern and carry as many generic container streams as you wanted. That's absolutely something we'll have to consider as we look at making terminal macros to work in the IMF space. For example, if you wanted to be able to use OPL to transition from one IMF application to another, or from one profile to another in the same application, it might be easier to do that if you had discrete MXF file macro rather than an IMF application-based macro. So the door is still wide open for multiple terminal macros and for the scope of those macros to be as narrow or as wide as necessary to satisfy the application. So as I said, audio labeling was super easy. 377-4 and all the labels in regXML already do everything we need to do. So as an example, in our terminal macro for DCP, if we want to supply a different sound field group label than the one that came in on the IMF, we just drop the minimal sound field group label into the DCP terminal macro description of the audio, and it will be parsed and read and dropped into the output MXF file. This is, again, the XML composition really paid off here because all this stuff already exists. All we had to do was refer to it in our schema, and as that project evolves over time, we won't have to do any maintenance work to follow it. It'll just come along for free as having been a reference. Obviously, implementations may have to change, but being able to go out and grab a complete audio labeling scheme that's compatible with IMF and use it directly in the expression of the process that makes that IMF is incredibly powerful, and is probably one of the most enjoyable parts of this system, because it was the most utility in the result for the least amount of programming and design work. I always love that. Another topic that's come up in this is, what is our wrapping strategy going to be? So specifically what I mean by wrapping strategy is, how do you decide what edit units from the source are going to go into what files in the output? I will start by pointing out, I don't think I have this on a slide anywhere, our implementation uses, maps rather, segments in the IMF timeline data model into reels in the cinema timeline data model. So if you want to have a particular composition in IMF, have a particular reel layout, a set of reels and layout in DCP, all you have to do is create a IMF composition playlist that has the segments in the right place. And our terminal macro will obey those and use those as boundaries for creating track files in certain wrapping strategy conditions. So this is an example of a graphic that's going to get better as this presentation makes its way through different conferences, but I'll try here. The top row is the MXF files in the IMF. The middle row is the segments in the IMF CPL, and the bottom row is the reels, or sorry, not reels, track files in the digital cinema domain. So this shows the preserve strategy. So what happens here is that the MXF files in the DCP world contain the same edit units as the MXF files in the IMF world. And so the DCP CPL is going to have to do whatever it needs to do in order to access those edit units. This contrasts with Flatten, where there is a DCP MXF file for every segment in the IMF CPL, and the edit units are just drawn into those. And so the difference between Flatten and Preserve really comes down to if you have, for example, an OV that you're doing picture inserts into, you want to preserve that level of granularity and normalization. You don't want to use the flatten strategy, because that'll just take every frame from your input MXF file and route it to some specific DCP MXF file that is dedicated to a particular reel in the DCP. If instead you use preserve, then the edit units from your IMF will appear next to each other in the DCP, and will create track files that have the same dimensions as what was in the source, which will make things like insert shots work much better. I don't know if this is particularly persuasive as a diagram. I hope to do a better version in the future. There's also another strategy called Monolith, where all the edit units in the source end up in one MXF track file. I'm hoping never to implement Monolith. I've seen its use in the IMF community cause all the problems that we were trying to avoid when we developed these schemes back for digital cinema. To me, it's an anti-pattern, but in the list of strategies one could have for mapping, it nonetheless, exists as a strategy one could use if one so chose. Local interaction. So as I mentioned a little while ago, the output profile list makes portable the description of all the processing to be done, but there are still things that are local to an implementation that can never be made portable, such as how that implementation looks up UUIDs to find assets, how that implementation interacts with cryptographic services. For the cinema application, we need to be able to encrypt track files, but for cinema and for IMF, we need to be able to generate signatures. And then, of course, the storage or transmission of the artifact that gets created. These three subjects will always have an implementation dependent aspect to them, and whether or not any of them can be assisted by information in the terminal macro remains to be discussed. We're currently experimenting right now, for example, with some flags. Wrong way. There we go. We're currently experimenting right in the terminal DCP terminal macro that would identify the crypto service to be used for encryption and for signature. But whether those would ultimately be something people need to have portable is a question yet to be understood. So as I mentioned earlier, going just from DCDM into DC super easy, from app2 into DCP, we're going to need some more tools. Specifically, we're going to need a color transformation, and we're probably going to need some cropping. All the ways that it could go wrong as well. And so I made a pass at what I'm calling the named color transform macro, or in this case, it's just simply called color transform. This uses dictionary labels of primary sets to describe the color transformation. So whereas with this, you could look at it and only know if it's right if you're good at memorizing constants, or if you stop to do the calculation yourself. With this one, you can look at it and pretty much tell it's right without having to think very hard. With this one, you can do any color space to any color space. With this one, you can only go between color spaces for which you have labels, although coming up with labels hasn't really been a problem. So I'm actually leaning toward this right now, and this is the one that I'm using. As I mentioned before, logging and error reporting is completely untouched, but for portability reasons, getting back good reports of why a failure occurred, good meaning that you can act on them and potentially resolve the error by supplying new materials, I think is critical to making this work. And so we're working on some proposed standard exceptions and proposed standard processing states to announce. So for example, what state was I in when the exception occurred? VirtualTrackld, I've been using that. That's really super handy for, I have a test matrix of all kinds of weird OPLs to make, or CPLs rather, to make sure that my OPL is ordering edit units correctly, and TrackID tells me when I did that right and when I did that wrong. I've also been playing with VirtualSequenceld, which is kind of what it says. which is very useful for recognizing an artifact that's already been generated. So if I associate a virtual sequence ID with a particular DCP file that indicated where in the IMF source composition it came from, and then along comes another IMF source composition that's, say, maybe a version file, but it uses some of the same sequences, for example, the same picture, I can recognize with sequence ID that I already had those artifacts and avoid generating them. So both of these, well, this, which we've talked about before, and this, which is a subset idea that I may have come up with myself or somebody might have told me about it, I don't remember, are both super important to making this system work in a larger integrated environment. Again, scaling and avoiding extra work are supported by these two features. So I've got some prototype macros I'm working on. In addition to the color transformation stuff, I've implemented a CDL style slope offset power operator. And of course, I have this digital cinema package terminal macro implementation. And that's it. So thank you all